Now that we have validated our algorithms in MIL, confirmed our software behavior in SIL, and verified a real-time performance on the actual processor in PIL, we are ready for one of the most powerful and critical stages in automotive testing, hardware in the loop, or simply HiL. HiL is where the real ECU hardware, the same one that will go inside the vehicle, meets a virtual world. It's the bridge between pure simulation and real world testing. This is where engineers connect their actual electronic control unit to a real time simulated environment that mimics the entire vehicle and its surroundings. The sensors, actuators, engine, wheels, brakes, and even driver inputs. In short, hill testing answers a crucial question. Will my real ECU behave correctly when it's finally inside the car? Let's break this down step by step. In a typical hill setup, the ECU, the real hardware controller, runs the embedded software just like it could in the vehicle. The plant model, which simulates the vehicle's dynamics, environment, and components, runs in real time on a dedicated simulation computer. The HiL simulators acts as a virtual car. It sends a simulated sensor data like wheel speed, temperature, throttle position, or battery voltage to the ECU and receives actuator signals like injector commands, PWM duty cycles, or relay triggers back from it. To make this happen, the simulator is connected to the ECU using real interfaces CAN, LIN, FlexRay, Ethernet, SPI, analog and digital inputs and outputs, and even PWM signals. The timing is real, the signals are real, but the vehicle is simulated. So you are testing the ECU as if it were installed in a car. Only you are sitting safely in a lab. Hill systems are typically built using specialized platforms like DSpace, IN Veristand, Vector VT systems, or ETA's LabCar. These platforms can run complex plant models, engine thermodynamics, vehicle dynamic, braking, electric drives, battery systems, all in real time. Now, why is IL so important? Because this is the first stage where all software, hardware, and communication come together under realistic conditions. You are testing the real ECU hardware, the actual compiled code, and the same network communication setup that will exist in the vehicle, but without needing the actual car or physical environment. This allows engineers to safely verify safety critical systems such as braking, steering, airbag deployment, battery management, or autonomous driving functions long before the prototype vehicle is ready. Let's take an example. Imagine we are developing an electric vehicle battery management system BMS. In a IL setup, the real BMS ECU is placed on the bench. The IL simulator provides virtual battery cell voltages, temperatures, and current readings. When the BMS commands a relay to open or close, the IL system reacts instantly by simulating the battery's electrical behavior. Engineers can simulate thousands of driving cycles, faults, and environmental conditions all without touching a real car. Now, let's look at what IL helps verify in detail. ECU functionality in real time, ensuring all control algorithms behave correctly under realistic operating conditions. I/O signal integrity, verifying analog, digital, PWM, and communication signals between ECU and simulated sensors actuators. Real time performance, checking if ECU tasks and interrupts meet real world timing deadlines. Communication network testing, validating CAN, LIN, FlexRay, and Ethernet message timing, IDs, and data consistency. Sensor and actuator interface behavior, ensuring signals match expected levels, scaling, and fault responses. Fault injection and diagnostics, simulating open circuits, short circuits, signal dropouts, and checking diagnostic trouble codes. Safety and redundancy behavior, verifying fail-safe transitions, watchdog recovery, and safe state entry. Environmental and load testing, emulating temperature effects, power supply variations, and sensor drift. Closed loop control validation, confirming that the ECU maintains stability, response, and performance in simulated vehicle conditions. Functional safety verification, ensuring compliance with the ISO 26262 safety standards through repeatable, traceable tests. Hill testing is also where fault injection becomes incredibly powerful. In real vehicles, you can't easily simulate a wheel speed sensor failure or a short circuit in the throttle signal. But in Hill, you can do this safely. Engineers inject faults like open or short circuits on sensor lines, voltage drops, communication timeouts on CAN or LIN, struck actuators or delayed responses. The goal is to confirm that the ECU detects and reacts appropriately. For instance, by switching to limp ohm mode, triggering a diagnostic code, or cutting off power to protect the system. HiL also supports test automation. You can run thousands of test cases automatically overnight. The system logs all ECU outputs, compares them to expected results, and generates a complete test report. This is essential for regression testing. Every time a new software version is released, it can be validated instantly against hundreds of predefined scenarios. Another critical advantage is reproducibility. In vehicle tests, road conditions and driver behavior constantly change. But in IL, every test can be repeated exactly the same way down to the milliseconds. This consistency is crucial when verifying timing behavior, safety functions, or compliance requirements. Let's also talk about real-time execution. Hill systems must operate in hard real-time, meaning they simulate the vehicle's dynamics at the same rate the ECU expects real signals. If the ECU runs a 1 kHz control loop, the Hill simulator must update all relevant signals every milliseconds without delay. That's why IL simulators use powerful real-time CPUs or FPGAs, ensuring deterministic timing and no latency, even for complex multi-domain simulations like hybrid vehicles or autonomous systems. Hill is also the stage where engineers verify network level integration. Modern vehicles have dozens of ECUs communicating over CAN, LIN, FlexRay, or Ethernet. Hill setups can simulate the entire in vehicle network. This allows testing of message prioritization, bus load, arbitration, and data consistency between ECUs before actual in vehicle wiring harness are built. Let's take another example, testing an electronic stability control or ESC system. In IL, the real ESC ECU is connected to a simulator that models the car's suspension, wheel speeds, brake pressures, and steering inputs. Engineers simulate emergency maneuvers like sudden braking or oversteer. The ECU responds by activating brakes and adjusting torque, and simulator reacts by updating vehicle motion in real time. This closed loop behavior shows whether the ESC logic correctly stabilizes the vehicle all without a single physical wheel moving. Hill setups can also integrate real hardware sensors or actuators. This hybrid testing is sometimes called semi-physical simulation. For example, you can use a real temperature sensor or current sensor connected to the ECU while keeping the rest of the system simulated. This gives even higher realism for critical components. When it comes to data analysis, IL platforms provide full traceability. You can record every signal, variable, and CAN message during tests. This helps engineers identify subtle issues like timing jitter, unexpected voltage drops, or incorrect scaling long before field testing. And speaking of safety, IL is absolutely essential for ISO 26262 compliant automotive software. It provides the test evidence for hardware software integration verification, safety mechanism validation, and fault tolerance checks. Every fault injection, diagnostic behavior, and recovery response can be documented precisely, something not feasible with real vehicle testing. HiL is also a key step in continuous integration for automotive software. Modern development pipelines automatically build software, deploy it to a HiL bench, run regression tests, and push results to dashboards. This speeds up development, reduces human error, and ensures consistent quality with every software iteration. Now, let's not forget cost and safety benefits. Running thousands of kilometers of virtual tests in HiL can replace months of expensive prototype vehicle testing. You can test rain, snow, extreme braking, or even sensor faults all safely and repeatedly in the lab. In short, HiL gives you the confidence that your ECU will work perfectly when it's finally installed in the car. Let's take one more example, testing an electric power steering or EPS system. The actual EPS ECU is connected to a HiL simulator that models steering torque, road feedback, and driver input. Engineers simulate lane changes, rough roads, and parking maneuvers. They verify that steering assist behaves smoothly, torque feedback is accurate, and no fault occurs under extreme loads. All of this before the ECU even touches a real steering column. To summarize, model in the loop mill, early algorithm design and simulation, software in the loop SIL, validating actual code in simulation, processor in the loop PIL, verifying performance on the real microcontroller, hardware in the loop HIL, testing the actual ECU in a simulated but in real-time vehicle environment. HIL is the final validation stage before vehicle level testing. It's where you gain full confidence that your ECU software and hardware work flawlessly, safely, and in real time, ready for integration into a real vehicle.